All right, we are recording. Okay, welcome everyone to the exam review for exam 2 in EECE 2310. This is for Professor Kogan and Professor Ahmed. I'm going to go through, I have a list of things prepared. If at any time you think something is too easy or too hard, let me know and we can skip to an example that helps you out. Of course, I'm not sitting in class every day, so I don't know exactly what your professors have said, but I do have their slides and materials that I've based this off. So let me know if anything is inconsistent with what you've learned in class, but otherwise this should be a pretty thorough review of the concepts that are going to be on your exam. That's, I think, this week, this Friday or something like that. So we're going to start off with talking about some different logic gates. So the XOR and the XNOR. And these are actually really useful gates for parity checking. So the XOR, if you have two inputs, this is what the truth table looks like. It's a 1 when exactly one of the inputs is 1, and it's a 0 otherwise. So it's like an OR, where this 1-1 case is a 0. Okay, it's like an OR like that. So this is in the 2-bit case, the 2-bit input case, where XOR is like that. When you get to multiple bits, it generalizes to have a 1 on the output when there's an odd number of 1s in the input. And if there's an even number of 1s or 0 1s, then the output will be 0. So if we look at this 2-input case, there's only one 1 on the input here, so the output is 1. There's a single 1 on the input here, so the output is 1. Otherwise, if they're both 1s or if they're both 0s, then the output is 0. Similarly, XNOR, of course, is just the inverse of that. So everywhere that there's a 0 for the NOR, for the XOR, there's a 1 for the XNOR, and vice versa. So what we can use these gates for and why they're so useful is the XOR, in a general case, checks for odd parity. So that means if there's an odd number of 1s in the input, then the output will be 1. So if we have a 3-input gate, there's going to be a 1 anytime there's an odd number of 1s on the input. So for XOR, if it's all 0s, the output is 0. Here we have 0, 0, 1. There's an odd number of 1s. There's 1, 1 on the input. The output will be 1. Similarly, 0, 1, 0 will give us a 1. 0, 1, 1 has an even number of 1s, so the output is 0. Okay. 1, 0, 0, that's an odd number of 1s. So we put a 1. 1, 0, 1 is a 0, because it's an even number of 1s. Similarly, this is 0. And when we have 3 1s on the input, that's also a 1. So this is the truth table for XOR in a 3-input case. And XNOR is going to be the opposite. So XNOR, if XOR checks for odd parity, XNOR checks for even parity, so an even number of 1s, where we say that 0 is even. So when the input is 0, 0, the output is 1. And if it's 1, 1, it's 1, otherwise it's 0. So in a 3-input case, we're going to be looking for an even number of 1s, or alternatively, just the opposite of the XOR truth table. So we can go ahead and fill in the 3-input truth table for XNOR. This is an even number of 1s, so it's a 1, even number, odd number. So you can use these types of gates in like input checking or in communications. You probably talked about a parity check being if you were to send a message between two systems and some errors can happen, like a bit can get flipped. If you sent the message and the message you sent had an even number of 1s, then you could put a parity bit that says like this is a 1 if there's an even number of 1s. And then the receiver, what they'll do is count how many 1s there are. And if it's an even number of 1s and the parity bit matches, then there's a good chance that the message was sent without any errors. But if something happened and maybe one of the bits got flipped and where there used to be an even number of 1s, now there's an odd number of 1s, then that parity bit is going to be different, or it's not going to match the message. So either the parity bit got flipped or some bit in the message got flipped. And that's a very simple way of error checking in these message protocols. So that's XOR and XNOR. The next thing that we'll talk about is universal gates. So you probably talked about how NAND and NOR are called universal gates, meaning that you can implement any logic, any combinational logic circuit using just NANDs and just NORs. And the reason you can do that is, let's say that we're going to do our NAND conversions. And conversions. So we have an inverter. The way that we write that in the NAND world is we just have the inputs tied together. And this is an inverter in the NAND world. Okay? An AND gate in the NAND world, is you take the inputs, NAND, and then invert them. So this intermediate step is like, if this is A, this is B, this is A, B, not, because that's what the NAND gate does. It says and not. Okay, and then what you do is you pass it through this inverter, which we just did up here. So this becomes A, B, not, not. The nots cancel, which is just A and B. Okay, and to do an OR gate in NAND world, we have to first invert both of our inputs and then pass each of those through a NAND. So when we're doing these types of conversion problems, and I can guarantee you that you will see a question like this on your exam. I can personally guarantee that. So make sure you know how to do these for the NAND and the NOR case, and we'll run through an example of each. Okay, so the question asks us to convert this circuit to use just NAND gates. So the first step that I like to do is like step one is just convert everything, okay? So don't worry about simplifications in this step. Let's make sure that the circuit is still on the screen. We'll take our A input and our B input. And B has an inversion bubble on the input, so we need to invert this. Okay, so we're going to do a NAND there. This is a NOT gate. This is an inversion. I like to box my conversions so that you know what's a part of what, and you'll see that in a little bit. Okay, so we're inverting B, so we've handled this inversion bubble. Now we have an AND. So we look at our chart. An AND means we pass it through a NAND, and then we invert the output. Here's our two inputs. Pass them through a NAND gate, and then we invert the outputs. Okay, so this whole block here is an AND gate. An AND gate, and you can just swap these in one for the other. It's exactly the same. Let's look at our C and our D. So C and D, neither of them are inverted, so we have to look at how do we do an OR gate, right? This is a NOR, but that can just be considered an OR gate followed by an inverter for our purposes. Okay. So if that's a NOR, how do we do OR? First, we invert both of the inputs. Okay, and then we pass the output to a NAND. So this is an OR. And then, of course, there was an inversion bubble here. So we have to invert a single time. The NOT gate, an inverter. Okay, so now we've got everything up until this last OR gate figured out. There's an inversion bubble on this side. So let's invert. Okay, and then we have to do the OR. Okay, so we've taken care of the inversion bubble. Now we basically have to OR these two lines together. And OR, again, we invert both of them and then pass them through to a NAND. So this is a big ol' OR, and this one is not. Okay, so this is how I like to draw them. Obviously, on my exam, I draw them a little bit cleaner so that the teacher can read, but I like to box the substitutions I've made, so that way you don't get confused on what belongs to what. Okay, so that's step one, is just convert it. Step two, of course, this is everyone's favorite part. You get to cancel out the unnecessary gates. So when we have two inverters in series with each other, we can cancel both of them out because it's doing a double inversion. So we ignore our boxes now, and we notice that at this line, we invert once, and then we invert a second time. So we can cross out both of these. Similarly, here on this line, we have a single inversion and then another single inversion, so we can cross out both of these. And I believe that's all the simplifications we can do. So the final circuit would be the simplified version of this. We have A, B, C, D. Single inversion here, going into NAND. This gate is gone. This gate is gone. Let's do our C's and our D's. Invert. This OR is still untouched. We've canceled out this gate and this gate, which means that at the end, oh, my mistake, we recently do invert this one. Cancel out this one and this one. So on this top one, we have a single inversion. And then these lines go into our final NAND, which is right here. So we've implemented this original circuit using only NAND gates. And sometimes you might be asked to determine whether the NAND gate conversion or the NOR gate conversion is more efficient. So we'll do the same problem with NORs in just a second, but we've used 1, 2, 3, 4, 5, 6, 7 NAND gates. Okay, so 7 NAND gates. We'll do next, looking at NORs. So we're going to need to know our NOR inversions, and they're very similar, and you should probably have these memorized because I don't know if you get a cheat sheet or anything. But if you know one of them, you can probably figure out the other, okay? So these are our NOR conversions. NOR conversions. So again, if we want an inverter in the NOR world, is where we tie our inputs together like that. It's kind of the same between the NAND and the NOR. Next, we want to do an AND. This is the one where we have to invert both of our inputs. Oh, sorry. We have to invert both of our inputs and then pass the result to a NOR gate. Okay, that's an AND. Then finally, an OR. Like that. OR is easier because you just pass in your inputs to the NOR and then tie them together and invert it. So this is like saying NOR and NOT, okay, which is just OR. Okay, so let's quickly do this example using our NORs. Use a different color here. So for NORs, first we'll start with our B has to be inverted. And to invert using NORs, remember we tie in our inputs together. And now we've got our AND gate. So an AND gate requires you invert both of your inputs. And you might see where we can already do a little bit of simplification, but just keep this the way that it is right now. So these two together get NORed together. And this together is our entire AND gate. Okay, whereas this one was just a. Okay. Next, we got our C and our D, and they're connected to an OR. Okay, they're connected to an OR. And OR is the one that's a little bit easier for NORs because you just do NOR and NOT. Okay, and there is a NOT on the outside, so we can tie our inputs together and invert it again. Okay, and then both of these have to go to this OR gate. So this top input is inverted from that inversion bubble. And then for an OR, we just NOR them together and NOT. Running out of room a little bit. Okay, so this is our last OR gate. This is a NOT. This one was our OR gate. And this is our NOT. Talking about this inversion bubble on this OR gate. And I know you might be able to recognize, well, this is already kind of a NOR gate, but in the general sense, it'll all work out even if you do a couple of extra steps because you'll be able to cancel. So I would say just think about it algorithmically. Don't confuse yourself. Try not to make any mistakes on these because these should be easy points. So we can go through into our cancellations. You can see there's 2 inverters in series here. And the way that you can tell is, for example, we cannot cross out these 2 because the one on the left is not acting as an inverter. It's taking 2 different lines as inputs, whereas the inverters are taking the same line split up as their inputs. Okay, that's what we mean when we're looking at gates that we can cancel out. So we cannot cancel out this 2 series pair because the one on the left is not acting as an inverter. So what else can we cancel? We can cancel out this knot and this knot that are in series with each other. Okay, and I believe that's it. So I'll spare you from redrawing this circuit without these gates because I'm sure that at this point you can do that. If not, we did it for the other case. We just redraw it without the ones that we've crossed out. Okay, so next, let's go on to some of our other components. And I know that you talked about these during exam 1, but I'm not sure to what extent you actually tested on them. So we're just going to go over muxes and decoders and encoders a little bit. And if you have any questions about them, then feel free to ask. But otherwise, I think knowing how they work and what kind of inputs and outputs they have, that'll probably be sufficient for your exam. So the mux has one output and several inputs. And what the mux does is it selects which of the input lines to pass through to the output. So it's kind of like, I think the analogy that they used in the book is you have like a railroad line with your railroad and you have like several tracks coming in and there's some kind of switch here. You can picture one of those big old switches like in the movies. And someone pushes the switch. Maybe he's got a little hat on. He pushes the switch to direct one track to come to the output. And so any train that's on this track will pass through to the output. So that's a mux. Just draw this on your exam, you should be fine. So the important thing about muxes is you have k select lines for 2 to the k inputs. So your number of inputs is generally going to be a power of 2. Technically, I guess it doesn't have to be a power of 2, but you're always going to have the capacity for up to a power of 2. So you might as well allow that many inputs. So your k select lines are going to be arranged in some binary number. So say we have this, we would call this a 4-to-1 mux because it has 4 inputs and 1 output. And so if the number of inputs is 4 inputs, this means that we will have log base 2 of 4 select lines. Okay, which is 2. We have 2 select lines that control 2 to the 2 inputs. And our possible k values will be 0, 0, 0, 1, 1, 0, and 1, 1. Those 4 cases we have. And we'll call this 0, 0, 0, 1, 1, 0, 1, 1. And whatever our select lines are set up as, that's going to determine which one of the inputs get passed to the output. So if our k's are 0 and 1, then that's this line is going to get passed to the output. So regardless of whether it's a 0 or a 1 on this line, the output is going to match the input. Okay, so we could call this, we could call our input lines like this could be I0, this one could be I1, I2, and I3. Just whatever is on those lines. So if our select lines are like this, our output is going to be I0, I1, I2, I3. So this is kind of the truth table for a mux. And so in addition to being able to pass through, pass inputs through to outputs, it's very useful in a lot of ways. You'll see when you take 3320, muxes can be used to kind of hard code truth tables. So imagine you have your inputs are your select lines. And what those are selecting is one of 4 different cases. So in this case, these are hard-coded values. So this line would actually just be connected to ground. This one would be connected to ground if there's a logic 0 there. And this one could be connected to your VCC. Okay, so this one would also be grounded. And this is not for this class, but this is just kind of an idea of what muxes can do, in addition to what they do up there, is you can have your select lines pick one of these cases, and that's basically implementing the truth table. So in this case, we've implemented and. So if A and B are both 1, then you're selecting this case, and you're going to pass a 1 through to the output. Otherwise, you're going to be selecting one of these other 3, and there's a 0. So that's kind of a neat little way to use muxes. And when you take 3320, if you haven't already, they're going to ask you to kind of implement a bunch of different circuits using only muxes. So just a little heads up there. Are there any questions so far? And this will be posted online after this video. And if you'd like this note deck, I can send that out as well. Next up is decoders. So decoders and encoders, it's easy to get them mixed up. But just try and remember what the input is and what the output is, and then you'll be able to kind of work backwards from there to figure out when to use which. So a decoder takes binary input and has 1 hot output. So it's like decoding a binary number. That's how I like to think about it. It's decoding a binary number, and it's kind of like spreading it out into one of many outputs. So if it has k inputs, it has 2 to the k outputs. Or alternatively, if it has n outputs, it'll have log base 2 of n inputs. So what the decoder does is it'll take some binary input. So say you have 3 inputs, and you would have 2 to the k is 8 outputs. Okay, so 3 inputs, 8 outputs. So, oh no. Oh, never mind, we're good. So if you have your k values could be, it's like k2, k1, k0. These are your 3 bits. Be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. So of course you're gonna be having 8 output lines. There's 8 input cases, and you have 8 output lines. And in this case, your output 0 will have a 1. Otherwise, they'll have zeros. So 1 hot meaning only one of the lines will be on or hot, and the other ones will be 0. So I think the analogy that you talk about in class for this one is a sprinkler system. So if you have maybe 8 sprinklers, and you only want to turn one of them on at a time, you might have a decoder. So you would put in, say I want to turn in sprinkler number 7. 7 in binary is 1, 1, 1. So these would be your k inputs. 1, 1, and 1. So we put a 1, 1, and 1. Then output number 7, which these are labeled from 0, 1, 2, 3, 4. The last one is 7. Output number 7 will have a 1, and all the other ones will have a 0 on them. And that's what the decoder does. Okay. The only problem with this is, well, okay, you only have one output is high at a time, right? So it really depends on your application if that's what you need. Otherwise, if you want some different combination, like in this case, I want both of these to be on, then you'll have to make your K-map, make your truth table, and implement a little more complicated logic. But the decoder, as it is, it has 1 hot output, which means that only one of the values is high. The encoder is similar. It's basically the same thing, but opposite. If you have k outputs, you have up to 2 to the k inputs. Alternatively, if you have n inputs, that means you have log base 2 of n outputs. So what this one takes is, and it takes in all of these inputs, and it'll output a binary number, basically. So you might think if it works exactly the opposite, it'll take 1 hot input. But the problem with that is that if you're making a system that's maybe sensing something and then converting a number to binary, you can't ensure that the input is always going to be 1 hot. Maybe you can based on your system, but you can't ensure it. So a lot of times what you'll hear is that this is a priority encoder. So instead of needing to have a 1 hot input, it'll just check whatever the highest priority one is. So say this is a high priority, and this is low priority. Okay, so maybe this is, we call this one input 0 and this is input n. Okay, so it'll say it'll encode the binary index of the highest priority one that's on. So say we had a 0 here, but a 1 here, and this is maybe input number 6. This one is 7. Then the outputs are going to say, well, 7 isn't high, so we ignore it, but 6 is high. Our input number 6 is high, and that's our highest priority one. So we're going to put a binary 6 on the output, which I guess if you flip this one way or the other, this might be 1, 1, 0 or 1, 1, 0, you know? But it's going to be taking whichever one is the highest priority and encoding it in binary, its index. So if the highest one was, if the largest priority input was input number 0, and all the rest of these were zeros, then our output would be 0, 0, 0, which is binary 4, 0. Okay, so you can have, for an encoder, you can have multiple inputs high, because it's really hard to avoid that in the real world. Avoid having your inputs being anything but 1 hot. But in practice, you know, we'll usually do a priority encoder where you're looking for the highest priority. And that way you don't have to worry about if both of these are high, because you're going to discard everything that's not the highest priority one. The other case is that if everything is a 0, that's usually considered an invalid input, because if the output 0, 0, 0 meant that all the inputs were 0, then what would the output be if we wanted to actually select for the 0 case? So we usually consider all of the inputs being 0 as invalid, because this output 0, 0, 0 is reserved for when this case number 0 is being selected. So that's kind of the little bit of tricky stuff about encoders, is that they're a little bit more finicky in that way, but you can implement them. I'm pretty sure in your class you probably talked about like the priority system, like maybe you have a bunch of different sensors and some of them are more mission critical than others. So you'll be sensing which one is kind of maybe triggering an interrupt or something like that. Okay, so that's encoders and decoders. I don't know exactly what kind of problems you might see on these. For this exam, you might have more problems based on the like binary numbers and stuff like that. But if you have any questions, just ask me and we can go over some examples maybe. But for now, I think if you understand how an encoder and a decoder works, and know the differences between the two, I think you should probably be fine for this exam. The next part is adders. So there's these two types of adders, the half adder and the full adder. And the big difference between the two is the half adder does not have a carry in bit. So you see that the inputs to the half adder are just your A and your B bits. And the outputs are going to be the sum. And this is the carry out. Okay. So this one's pretty easy to understand because it doesn't really worry about if it's being chained together because there's no carry in input. But the full adder does have a carry in. So this is basically adding 3 bits together, whereas this one is adding 2 bits. So it might be the case that if you had a ripple adder or something, the first one might be a half adder because there's going to be no carry in, but then the other ones will need to be full adders. Right? And we'll show an example of that later. There's a couple of larger adder chains that you're going to need to know about. So that's the big difference. So the full adder, one other thing about the full adder is the logic for the carry out. So our cases for if we had 3 bits of input, we could have all zeros, and the output should be 0, carry 0. We could have a single one, and the output should be 1 carry 0. We could have 2 1s, and of course the order doesn't matter. It could be 1 0 1, and this is for the full adder. We have 1 0 1, and the output should be 1 carry 0, or 0 carry 1. And if we have all 3 1s, then the output should be 1 carry 1. So if we look at these bits separately, we see that the sum bit, which is this right-hand side bit, is 1 whenever we have an odd number of ones in the input. So in this case, we have 0 1s, this we have 2, in this one we have 1, and this one we have 3. So when there's an odd number of 1s on the input, the sum bit is 1. So that's why they use an XOR gate here, which we talked about earlier. The logic for this bit, the carry out bit, is a little more confusing. Look, there's 3 AND gates and an OR gate. So what this one is looking for is each of these AND gates basically represents the combination of one pair, either A and B, A and carry in, or B and carry in. And so it's checking, do we have at least one case where there are 2 bits high? Because the carry out bit is 1 in these 2 cases, where we have either 2 or 3. So what this logic is checking for is, do we have at least 2 1s in our input? And that's the carry out bit. And the sum bit is just the XOR. So that's kind of the inside of this full adder. I'm pretty sure as long as you understand that the full adder takes in 3 bits and has a carry out and a sum bit, whereas the half adder doesn't take in the carry in bit, then you should be good. You're gonna have to look at we'll look at the adders and shifters and the other more complicated adder circuits in a bit, but let's move on to the number systems. I think that's a bigger part of this exam, or maybe a little bit of a more confusing part of the exam. So I know we talked about 2's complement for the last exam, but I don't think we talked about some of the other ways to represent negative numbers, and we didn't talk about floating point numbers. So to represent unsigned numbers, it's easy, right? That's normal binary. That's where we have n bits, and we can represent anywhere from 0, which would be all zeros, to 2 to the power n minus 1. Okay, this is normal binary, so if we have 3 bits, we can represent anywhere from 0 to 7, that'd be 0, 0, 0 to 1, 1, 1. So on a number line, that's kind of what this regime looks like. So if we have 3-bit unsigned integers, we can represent anywhere from 0 up to 7, and that's a total of 8 numbers. So the idea behind a signed number system is we would want to represent the same number of numbers using the same number of bits. But we would want that our representation of negative numbers allows us to perform arithmetic, because that'll make it easier for computers to do their jobs. So what we would do is then we would, what makes the most sense if we were to design some numbering system might be to just shift this range. Instead of going from 0 to 7, maybe shift it this way a little bit, that we represent maybe from -4 to +3. So there's a couple of different numbering systems, and I know on your slides and your notes from class, there's a really good visual of all the number lines for all the different numbering systems. But we'll kind of just talk about 2's complement for the most part, because that's the one that you'll be using. Real quickly, the other one, sign magnitude. So this is maybe the most naive way of doing it, where you have a sign bit and a magnitude bit. So if +7 is 0, 1, 1, 1, then -7 is 1, 1, 1, 1, where the only thing that changes is the sign bit, and this part that represents the magnitude, that doesn't change. So the advantage of this system is it's very simple for you to look at this number and say, okay, this is a 7, the sign bit is 0, so this is a +7. Otherwise, it's a 7 with the sign bit is 1, so that means this is a -7. Okay, it's really easy for us to read. The problem is that one advantage to kind of a numbering system of like some sign number system is you would want that 7 plus -7 gives you 0. okay? And if we were to just do this addition, 0, 1, 1, 1 plus 1, 1, 1, 1, 1 carry 1 plus 1 is 0 carry 1. 1 plus 1 plus 1 is 1 carry 1, 1, 1, 0. Okay, so if we look at this, if we discard the overflow, 0, 1, 1, 0, that is not 0. So to do arithmetic using the sign magnitude system would require that you do a little bit of conversion before you can just add the bit strings, because it's not giving us the desired behavior where 7 plus -7 is 0. At least not if we define 0 in this way. And another drawback of the sign magnitude system is that you end up with 2 0 strings, because there's +0 and -0, because the magnitude would be 0 and the sign can be whatever it wants. So that's a sign magnitude system. You probably won't see this very much after this class, but you might see it referred to in literature. So it's good to know what that means. But the disadvantage is it's harder to do arithmetic using those numbers. One's complement is you just simply do the bitwise inversion. So example, if 7 in base 10 is 0, 1, 1, 1, -7 is you just flip every single bit, 1, 0, 0, 0, 0. And this is kind of more similar to 2's complement because you have this step, but you don't add 1 at the end. So what that gives us is we also have 2 zeros. Or if we try 7 plus -7, that's 0, 1, 1, 1, plus -7 is 1, 0, 0, 0. No matter what numbers you choose with this, you're always going to get a string of all ones when you add the additive inverses of each other. So that means we're going to say that this represents 0, but then clearly so does this represent 0. Okay? And if you apply this bitwise inversion between these two, you get 1, 1, 1, 1 converts to 0, 0, 0, 0 when you flip all the bits. So in this case, we also have 2 zeros, which is not ideal, right? We would want to make the most use of the number of bits we have. We don't want to be able to represent the same number in 2 different ways, because then, I mean, that leads to all sorts of problems. If you're trying to check for equality, you have to check whether both of those cases are true or false. So this system is not the best. That's where we landed on 2's complement. So 2's complement is where it basically revolves around the idea that if you take x plus -x, you're going to get a string of all zeros, okay? So a -x is defined as the string that when added to your x gives you a string of all zeros, okay? And so I hope by this point you're a little familiar with 2's complement, because we did this in exam 1. But one big thing that you'll need to know for this exam is sign extending. So if you have a positive number, you can always add leading zeros to a signed number, and that's pretty intuitive. But for a negative number, you can always add leading ones. Okay, and you can check this to make sure. Here's one example where we have a +4. The number of zeros up front doesn't matter. But we have a bunch of leading ones, and we try and convert this back to let's convert this back to a positive number. So we flip all of these bits, 0, 0, 0, 0, 0, 1, 1. When we add 1, then we will, of course, get our +4 being 1, 0, 0 with leading zeros. Okay, so this is important to know. And here's kind of a representation of like a visualization of the 2's complement system. So here's where you can kind of see, this is with 4 bits, how the numbers are related to each other. If you kind of go in a clockwise, that's normal binary counting, 0, 0, 0, 0, 0, 1, 0, 1, 0. And so we have up to -8. This is where it kind of flips around and starts counting down, and the negatives gets back to 0. So maybe seeing it laid out like this can help you understand why 2's complement is so good, because we only have 1 0, and it's the one that makes sense. It's all zeros. The string of all ones is not 0, as it was in the 1's complement. So we're making more efficient use of the number of numbers that we can represent. We're using every single one of them to represent a unique number. The disadvantage, of course, is that we have a -8, but we don't have a +8. But that's just one of the drawbacks of this system. Okay, so up to this point, are there any questions? Anything that's confusing? Because we're going to get into our binary multiplication and arithmetic. I think that's probably the part of the class that is the part of this exam that's the most confusing. Check the online. Good online? Okay. So let's get into our binary multiplication. So binary multiplication is a lot like decimal multiplication. So if we were going to do negative 30 times 7, so negative 30 times 7, we start with the rightmost digits, and we do 7 times 0 is 0. 7 times, well, okay, I guess usually when we do this, we kind of ignore the sign and add it at the end. 7 times 3 is 21, and this is our number, and it's negative because it's a negative 30. Okay, so it's a lot of single digit multiplication, and then you add at the end. So if we had 30 times 17, right? The first thing we would do is we would do 7 times 30, which is 210, and then we add our 0 here, and then we do 1 times 30. So 1 times 30 is 30, right? So this would be our answer. So in binary multiplication, the nice thing is that when you're doing decimal multiplication, you have to know what 7 times 0 is. You have to know what 7 times 3 is. You have to know 1 times 0 and 1 times 3. In binary multiplication, say we have a string that looks like this, times 1, 1, 0, 1. The only cases that we have is 1 times 1 is 1, 1 times 0 is 0, and 0 times 0 is 0. So what you're gonna notice is that if you look at the numbers, these partial sums, or these partial products, the first one was 210, and the second one was 300. When we're in binary multiplication, the partial products are always just going to be this first number. So let's do this multiplication. We just do it bit by bit. So 1 times 1 is 1, 1 times 0 is 0, 1, 0, 1, and 1. Okay, so if you notice, this is our original number. And then let's put our 0 in here and do it again. So next we have a 0 times everything. So this is going to give us all zeros. That's not really helpful. But let's do it again for this one. We put 2 leading zeros, and then perform our multiplication. We do 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, 0, 1, 1. So if you notice, this is also our original number, just shifted over by 2 places. So if you can guess, the result of the third partial product is also just going to be our original number shifted over by 3. So 1, 0, 1, 0, 1, 1. Let me highlight what I'm talking about here. This number gets replicated down here once, twice, and 3 times. And if you notice the pattern here, once, twice, and 3 times in, let's call this position 0, position 1, 2, and 3. This is exactly where the 1s showed up in our second number, position 0, position 2, and position 3. So this is kind of the trick to binary multiplication that's going to let us implement this using just adders, because when you do this sum, you're only going to be adding bits, and those bits are the result of this basically what is essentially a bitwise and. 1 times 1 is like 1 and 1. Okay, so that's kind of getting a little bit ahead. Let's just perform this multiplication, negative 30 times 7, in binary. So the first step is we need to get our numbers in binary. So 30 in binary is what? So it's 16 plus, well, let's just write it out. 30 in base 10 is the same as 16 plus 8 gives us 24, plus 4 gives us 28, plus 2 gives us 30. Okay, so this is 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. And there's no 2 to the 0. So we can say that this is 0, 1, 1, 1, 1. Let's give it a leading 0 just for good measure. Okay, so this is a 30 in base 10. A negative 30 in base 10 is we flip all these bits 1, 0, 0, 0, 0, 1, add 1, 1, 0, 0, 0, 1, 0. Okay, this is our negative 30. Let's get our 7 in base 10 is just 1, 1, 1. Right, and we can do a leading 0 to show that it's positive. So here's our numbers. Negative 30 is 1, 0, 0, 0, 1, 0. 7 is 0, 1, 1, 1. Get rid of that for now. We're multiplying. So the result of this multiplication is going to be longer than either of these two are. So this one is what? 1, 2, 3, 4, 5, 6 bits. This one is 3 bits. Okay, and we can call it 4 bits, and we'll see that it doesn't really matter as long as we have the core of it. So 4 bits and 6 bits. When we do this multiplication, we're going to get something that is 10 bits when we do it this way. Okay, so if we do this multiplication out, we get 1, 0, 0, 0, 1, 0. A leading 0, we also get 1, 0, 0, 0, 1, 0. And I'm just looking at it again. When there's a 1, it's going to go copy this number. When it's a 0, it's not. Put 2 leading 0s there, and we get 1, 0, 0, 0, 1, 0. So that's just the result of this multiplication, where this one, and this one are just the padding zeros. And if we wanted to, we could do the multiplication for the 4th step, which is all zeros. Okay, add these up, we get 0, 1, 1, 1, 0, 1, 1, 1. Okay, and it's kind of messy, but you'll see that, well, what do we know about our number? We know that it should be negative, and it should be 10 bits when we do it this way. So we look at the first 10 bits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And, whoops. Let me redo this. We look at the first 10 bits, and that's where we stop it. So in the general sense, if the two binary numbers are m bits and n bits, then you have to sign extend to make sure that they're the same length, and then then you reject anything past the m plus n partial products. Okay, so what I should have done is sign extended this one to start with, and we need to sign extend to 10 bits. My mistake. So remember, if we have a negative number, we sign extend using ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the 7 goes to 1, 2, 3, 4, 5, 6, 7, 8. Okay, there we go. So you do this multiplication, and I'll spare you all these steps because it's going to end up being just the kind of the same product. But whatever you get is going to be the result of your multiplication. So you can convert that back into decimal, and then that'll be your answer. Okay, and I think the binary multiplication is an easier part. We can do more examples if you'd like, but the binary fractions, I think, are where we're going to have to spend a lot more time. So let me know if you have any questions about the binary multiplication, but we'll move on for right now and do fractions. So this is kind of a weird concept that might be unintuitive at first, but it really is quite natural when you think about it. So on the left-hand side of the radix point is what we call it in the general sense, regardless of base. Be the binary point if we're in binary, or the decimal point if we're working with the decimal system. So in binary, right, to the left-hand side, we have 2 to the 0, 2 to the 1, 2 to the 2. But on the right-hand side, we extend this to the realm of the fractions by using the negative exponents. So whereas on the left-hand side, our exponents start counting up from 0, 0, 1, 2, 3, 4, 5, 6, 7. On the right-hand side, they start at -1, -2, -3, and you'll get these fractions. So 2 to the -1 is 1/2, 2 to the -2 is 1/4, 2 to the -3 is 1/8, and so on. So in the same way that on the left-hand side, if there's a 1, then that means that this power of 2 is part of your number. You can add it to recreate your number. It's the same way on the right-hand side. So if we have a 1 in this position, then that means that this power of 2 is a part of our number, and we can use it to add up and recreate our number. So for example, the decimal number 0.5 would be represented as the binary number 0.1, because it's 0 copies of 2 to the 0 and 1 copy of 2 to the -1, okay, which is 1/2, which is 0.5. This is a simple case, and this is kind of how we extend this concept of binary to include fractional numbers. Okay, so what you'll notice when you do this is that some numbers, the classic example is a decimal 0.1, which is 1/10, cannot be represented using a finite number of binary digits. So if you try, you might think, okay, clearly 0.1 is less than 0.5, so we can't include that. We can't include 0.25, we can't include 0.125, but we can include this 0.0625. Okay, so we've got 0.0625. And what we're trying to do is get a collection of powers of 2 that when we add them up will give us 0.1. And if you try and do this, you'll maybe get this one in there because it's 0.6 plus 0.3 is about 0.9. You'll try and do this, and you will never get exactly 0.1. You'll always have a little bit of error. And if you think that that means that decimal is an inherently better numbering system, because you think in decimal we can represent anything, there are some numbers like pi, like e, that we cannot represent using a finite number of digits. So it's really the same concept. If we were working in base pi, we could represent pi like this in base pi. But so no numbering system is inherently better or worse in this regard. It's just that some numbering systems can represent certain numbers and some of them can't. So you'll notice that when you're doing these problems, sometimes your professor will say, calculate this number, or like convert this fraction. Let's say we had like 7.825. They'll say convert this fraction to decimal or to binary with up to 6 bits on the right-hand side of the decimal point. So it's using a certain number of accuracy, which is 6 bits. And maybe your professor will specify a different number, or they'll tell you what kind of error is acceptable in your estimate. But you're not always going to get a perfect solution. So the algorithm for kind of converting decimal fractions to binary fractions. Your professor should give you two methods. One of them is the subtraction method, and the other one is the multiplication method. So for the subtraction, either method, it starts out with you first convert the left-hand side. So you ignore the fraction part, and you look just at the left-hand side and say 2. Well, how do I get binary 2? That is a 1, 0. Okay, and now we're in binary world. The next part you look at is this 0.9875, and you think about your powers of 2. So we can look back up at what those powers of 2 are. We just copy these. Okay, so here's our powers of 2. And you'll say 0.9875. If we do 0.9875 minus 0.5, we get 0.4875, which is a positive number. So we can include a 1 in the slot for 0.5. We'll do that with the next number too. So the next power of 2 is 0.25. So we just subtract 0.25. Okay, and what do we get? 0.05732. 0.2375. Okay, next we want 0.125. We can subtract 0.125. Oh, and don't forget, put a 1 for the 0.25 case. And we subtract 0.125, which represents 2 to the negative third power. 5, 2, 1, 1. 0.1125. So we'll put a 1, 0.125. And then we'll do one more. 2 to the negative 4 is 0.0625. So we subtract out 0.0625. We get what? 0.05. We'll put a 1 for 0.0625. And our remaining fraction at this point is 0.05. Okay, so that's going to require that we keep going. So we would subtract 0.03125, and we get left with a little bit, and then we'd maybe subtract 0.015625. This is a subtraction method, and the disadvantage of this method is you have to know these powers of 2, which is not that difficult to figure out, but you have to know what to subtract each time to know whether it fits into this number. So for this example, we just went to 4 bits, but you could keep going for however long you need to. The multiplication method might be a little bit easier. So you start out doing the same thing, where 3 gets turned into a binary 1, 1. And then you put your binary point. And now you're looking at the fraction part, so 0.1415. So what you do is you multiply this by 2. 2 times 1 is 1, plus 1 is 3, 8, 2. You multiply it by 2. And if this number is bigger than 1, then you put a 1 for the first power of 2. Otherwise, put a 0. So what we did is we multiplied it by 2. Our result was less than 1. So that means we do not put a 1 for the 0.5 case. Okay? So we try this again. We multiply this number by 2 times 2, 0, 6, 5, 6, 6, 0. So this is less than 1. So we put a 0 for the 0.25 case. Multiply by 2 again. And we get 1.1320. So we do have a 1. So that means we put a 1 for this 2 to the negative 3 case. And then we continue after discarding this 1 and continue with the rest of the fractions. 0.1320 multiplied by 2, 0, 4, 6, 2. And this is less than 1, so we put a 0. So I think this method is easier. You can continue going for however many decimal points you need, or how many binary points you need to your desired accuracy. But I think this method is easier because you don't need to remember all the powers of 2. And you could just write down and make yourself a key, but this method is probably a little bit simpler in the general case. So those are 2 methods of converting a decimal number or a decimal fraction into a binary fraction. To do the other way around, what you could do is just go through your number line and add up these powers of 2. So if it's 101.00011, you'd say this is 2 to the 2 plus 2 to the 0 plus 2 to the negative 4 plus 2 to the negative 5. So this is one way of doing it. The other way, this would, I mean, if you have a lot of 1s, this could be a lot of things you need to add, and who knows what 2 to the negative 5 is off the top of their head. So maybe a simpler way, or a different way, I should say, is to first convert the number to hex. So converting a number to hex, you start by grouping the bits into groups of 4, starting from your radix point. So start going from the left to the right. So one group would be this one. Another group would be this one. And then our last group would be this one. We can add in zeros on the left. And we also group to the right. So this group, and this group. And we're on the right-hand side, we can pad zeros on this side. So what you do is you convert each of these groups into a hex digit. So if you remember your hex tables, the binary number and hex, 0 maps to 0, 1 maps to 1, and you keep going, everything's the same. 9 in binary is a 9 in hex. But then a 10 in binary is an A, 11 is a B. I'll just write all these out. 12, 13, 14, 15, C, D, E, F. So if you're not really comfortable with hex, you should get comfortable with hex because you'll probably need it later in this class, but definitely if you ever take computer architecture, you'll need to know hexadecimal and other classes as well. So let's look at this group, 0, 0, 1, 0. That is a 2. 1, 1, 0, 1. Let's see, this is 8 plus 4 is 12, plus 1 is 13, and a 13 is a D. A D, 0, 1, 1, 0, that's 6. 1, 1, 0, 1, that's another D. 1, 0, 0, 1, that's 9. 0, 1, 1, 0 is 6. So this is a hex number, which is 2D6.D96. And now instead of grouping together or adding together all these powers of 2, you only have 6 different powers of 16. So what this number represents is 6 times 16 to the power 0 plus D, which is 13. 13 times 16 to the power 1 comes from here, from there, plus 2 times 16 to the power 2. Now the right-hand side of the decimal point is the same thing, plus D is 13 again. 13 times 16 to the negative 1, plus 9 times 16 to the negative 2, plus 6 times 16 to the negative 3. And then you only need to calculate this many things, whereas for this one we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13 powers of 2 that you need to add together. So if you feel comfortable working with hex, this is probably a better way to do it, and you might be asked to do this on your exam. So make sure it's important that you start grouping bits, starting from the radix point, going the left hand to the right. And if you need to pad to make a group of 4, you can pad zeros onto either the far left or the far right to make sure that it's an even group of 4. Okay. Next thing is negative binary fractions. So negative binary fractions, it works the same way as finding negative binary numbers. You find the positive binary fraction, flip all the bits, and the only different part is you add 1 to the least significant bit. So let's see what that looks like. So we want to write negative 8.625 in binary. So we start out by saying, what's 8.625 in binary? Step 1 is we represent 8 as 1, 0, 0, 0. 0.625. We can, let's do subtraction for this. We can multiply out, we can subtract out 0.5, which represents a 1 in this position, because we're going to be left with 0.125. We cannot subtract out we do minus 0.25, then we'll get a negative number. So we can't subtract out 0.25, so we'll put a 0 there. But the next power of 2 is 0.125. We can subtract 0.125 and we're left with a 0. So that means we put a 1 here because 0.125, which is 2 to the negative 2, was, or 2 to the negative 3, was part of it. This is 2 to the negative 1. Okay, so this is our number in binary, the positive version. Okay, and this can have, leading zeros out front. So if we want to change it to negative, we can flip all these bits. We can say 1, 0, 1, 1, 1, 0.010. Okay, and then we add a 1 in the smallest spot, the rightmost bit. So we're not adding a 1 to this value anymore. We're adding a 1 to the far right, which in this case is 0.001. Okay, and this gives us 1, 1, 0, 0.1, 1, 0, 1. So this is our number. This is a negative 8.625 in binary. And you can always double check. So our original fraction was 0, 1, 0, 0, 0, 0, 1. If we add our negative version, 1, 0, 1, 1, 1, we should get a whole bunch of carries when we add this, and it should end up being 0. 1 plus 1 is 0 carry 1, 0 carry 1, 0 carry 1, 0, 1, 0, 1, 0, 1. 1 plus 1 is 0 carry 1. 0, carry 1. And if we look at just the bits we were looking with before, these are all zeros. And we discard the overflow bit. So this is a way to ever check yourself if you're not sure on how you've made a number be the negative form. Add it to itself. This is a 8.625 minus 8.625 basically. And you should end up with zeros. Okay. Next we have a little bit about floating point numbers in the computer. So you might see this notation, this fixed point notation, where you have a Q, an N, and an F. So what this means is that you're dealing with a floating point number, right? So you're going to have a fraction part, but it has n total bits, and f of them are reserved for the fraction. So for example, if you see Q 8.3, that means you have 8 total bits and 3 of them for the fraction. So that means that there's 5 for the left-hand side for the actual integer part. Okay, and we know from our rules for multiplying that you're going to need more bits to store the product than you will to store each of the multiplicands or something. So the way that it'll expand is actually pretty intuitive. So if you multiply Q 8.3 times Q 8.3, so these would be two numbers that each have 8 total bits, 3 of them for the decimal. So 1, 2, 3, 4, 5, 3. So both of the numbers look like this. It doesn't really matter what's in them, but you're going to end up with a number of fraction bits equal to this number plus this number. So in this case, they're the same amount. So you're going to end up with 3 fraction, leaves us with 6 fractional bits. And the total number of bits will also get doubled. So 8 plus 8 is 16 total bits. So the result of this will be a number that has 10 bits for the left-hand side and 6 for the right-hand side for the fractional bits. So these are the fractional. And these are for the integer part. So, and another example is if you had, like, if they weren't the same number, right? Q 4.3 times a Q 2.1, the total number of bits, 4 and 6, get added together. This would be a Q, the result would be a Q 6.4. So we have 6 total bits, and 3 plus 1 equals 4 of them are for the fractional part. So you can perform the multiplication and count, but knowing how many bits to expect is good so you know where to stop counting the overflow. So if you have any sign extension that was unnecessary, you know when to cut it off. So I would imagine that you might have a sort of question that's like this, where they give you a standard. And if you're multiplying these two numbers, they're probably going to be in the same fixed point notation, the same standard. So that's why I showed this case where they're the same one. But just in the general case, know these rules that the total number of bits is going to be the sum of the total number of bits for the inputs. And the number of the fraction bits is also going to be the sum of the number of fraction bits, the inputs. So next, we're going to talk about the IEEE 32-bit floating point standard. So it's actually not as complicated as it might sound. There's just a couple of steps that you need to remember. So this is kind of what it looks like in the computer. You have 1 bit for the sign, 8 for the exponent, and 23 for the mantissa, or that's what we call the fraction bit. So it stores it in scientific notation, which, if you remember, is where you have like 1 bit to the left-hand side, and then the rest of it is just in fractions, and then you have times 10 to the something. That's in decimal. When we're in binary, the exponent is going to be 2 to the power something. And we're going to have a 1 point something, 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 something. Now, another difference between decimal and binary is if we're working in decimal, we could have a number like 6.626 times 10 to the negative 23rd, which is like Avogadro's number or something. But if you notice, is that what it is? 6.283, whatever. So we notice that the digit that's to the left of the decimal point could be a 6, but it could also be a 7. It could be an 8. It could be a 2. So there's a lot of different digits that could be here. But when we're working in binary, if we've normalized something to scientific notation in binary, the only possibility is that we have a 1 here. Because if there's a 0 here, then that means we have to keep shifting the binary point until we get a 1. Okay? So that's one key insight that lets this standard work so well, is say we have a number like 1001.011. To write this in scientific notation, we would move the decimal, or we move the binary point 1, 2, 3 places. We get 1.001011. We've moved it so that we have just a single 1 on the left-hand side. Now, if the computer knows that no matter what the number is, there's going to be a 1 right here, then it doesn't have to waste space storing that 1. So we have this kind of implied 1 in this IEEE standard. So this 1 is not going to be stored in the computer. All it's going to do is store this part. And that gives us an extra bit to store using 32 bits. So that's one little clever way in this standard that they save some space. But to use this standard, which there might be a question like this on your exam, is first you just convert it to the binary fraction. So you can ignore the sign when you do this because the IEEE standard is kind of in the sign magnitude form, where we do have a single bit that says the sign, and then the rest of it is just the magnitude of the number. So step 1, convert the number to a binary fraction and ignore the sign. Second step is normalize it in scientific notation. So get it in this form where you have a single 1 to the left and everything else is to the right. And then make sure you know your exponent. So in this case, we did 1, 2, 3 steps to the left. So this would be times 2 to the power 3. Because if we were going to move the point 1, 2, 3 steps to the right, then we would arrive at our original number. So the base in this exponent is 2 in the case of binary. Okay, so this is our number in scientific notation. There's another weird step that you have to do, is add 127 to the exponent. So there's a reason for this, and the reason is a little bit out of the scope of this class, but basically it comes down to they wanted numbers to sort in the same way for this floating point system. Like if you were to convert this to actually the floating point number, and you had a list of those numbers, you'd want them to sort the same way without having to convert them to floating point numbers. So the actual bit strings will sort out nicely when you do it in this way, and you don't use 2's complement for the exponent. So just remember this step. You have to add 127 to the exponent. So 3 plus 127 is 3 plus 127 equals 130. Okay. That's the next step. And then you have to make sure that when we're storing this, right, everything's going to be in binary. So convert 130 to binary, which would be 128 plus not 64, not 32, not 16, not 8, not 4, 2, not 1. This is 130 in binary. And we need to make it 8 bits. This is 1, 2, 3, 4, 5, 6, 7, 8. So we don't need to do anything there. That's our 8-bit exponent. And the sign, to say we're working with this number, the sign, we'd say that this is a positive number. I guess I didn't tell you what the number was. The sign bit is a 1 if it's a negative number, and a 0 if it's a positive number. So at this point, once you've done all this, you have the sign bit, you have the exponent bit, and then the mantissa bit, or the mantissa part, is just the part that's to the right of the decimal point, or the binary point, sorry. So, for example, this is our mantissa, 0, 0, 1, 0, 1, 1. And we need to make this 23 bits. So we would add on zeros to the right-hand side until we get 23. Okay? And that's the process. And it seems a little arbitrary with the adding 127 to the exponent, but just don't forget these steps. You might have to do this on your exam, but the process is very straightforward. You don't even have to worry about 2's complement really, because this is in the signed magnitude type form, where we don't flip the bits or anything. So if you can handle this, you should be fine. So converting it the other way, of course, is just a matter of splitting up the bits. So the leftmost bit is the sign bits. This is our sign, which indicates that it's a positive number. Next, we have 1, 2, 3, 4, 5, 6, 7, 8 bits for the exponent. And then this is the mantissa, or the fraction part. So the one step that you have to do is convert this exponent to a number, and then you have to subtract 127. So what do we have right here? This is 2 to the 0, 1, 2, 3, 4, 5, 6, 7. 2 to the 7 plus 2 to the 1, 0, 1, 2. Okay? 2 to the 7 is what, 128? Plus 4, 132. And then you minus 1, you subtract 127. We've got 5, 0, 0. So this number would be a positive number. It would be something times 2 to the power 5. And that something is the mantissa. So our mantissa is 1, 0, 0, 0, 0, 0, 0, 0, 1. So remember, there's an implied 1. So our binary number actually looks something like 1 point and then your mantissa. So 1, 0, 0, 0, 0, 0, 0, 1. Okay. So what you can do is write this as this times 2 to the 5. Okay. That's 1 dot mantissa. We can move the binary point back. So actually apply this times 2 to the 5. 1, 2, 3, 4, 5 places. 1, 1, 0, 0, 0, 0, 0, 0, 1. And here we have a binary fraction that we can convert to a decimal fraction using the same process that we did before. Okay? So I won't go over those steps again, but they're here and you should have them. Basically, you just convert this part and then you add your powers of 2, or you could convert it to hex and do it that way if you prefer. But that's how you get from IEEE to a decimal number, and then vice versa. Okay, I think the last thing on floating points is adding and subtracting. So if we have two scientific notation numbers, like 1.0100 times 2 to the 6 plus 1.1101 times 2 to the 3, we can't add these directly without making sure the exponents are the same. So one thing we can do is make sure the exponents are the same. So we can move this one over 3 spots. So this becomes 1010.0 times 2 to the 3. And this one is still 1.1101 times 2 to the 3. And then we can add the numbers normally. 1011.1101 times 2 to the 3. So make sure you line up the radix points, and then you can add normally as long as the exponents are the same. And this is the same thing in decimal that you've probably seen before. If you have 2.75 times 10 to the 3 plus 8.62 times 10 to the 2, then what we can do is we can convert these. This is really 27.5 times 10 squared plus 8.62 times 10 squared, and then you can add them. So really nothing special. Just remember that these same rules apply in binary as they do in decimal. And then for multiplication and division, if we wanted to instead multiply these numbers or divide them, right? We would multiply the base part and we would add the exponents. So I won't do this multiplication, but it would be the result of this multiplication times 2 to the 9, because we have 2 to the 3 plus 2 to the 6, 2 to the 9. Okay, and then we would just multiply these numbers like normal. So it's really not anything crazy. Just make sure that you're not getting messed up when you're doing these multiplications. You're not dropping any bits or anything, but the actual process is not that difficult. Just a couple more things to talk about. One hot encoding, we already mentioned this, but make sure you know what this is. It means that exactly one bit is 1 and all the other ones are 0. This is useful in memory for addressing. So maybe say you have a decoder, which takes in binary input, which could be like an address in memory. And the output will be a one hot vector that points to that block of memory. So we might have a 1 on this, and that could be like the read signal on a flip-flop. Okay? So that's a one hot vector, and remember, decoders output a one hot vector. Adders and subtractors. So this is an important circuit. You've probably seen this before. The idea behind this is that it can do both adding and subtracting by having this add subtract control. And what this line does is it inverts the B number by doing XOR, which basically inverts the numbers, and adds a 1 if you're subtracting to the carry in. So usually we have A3, A2, A1, A0 plus B3, B2, B1, B0, right? So this is like in the normal case. If we want to subtract, then what we need to do is invert all of these bits and add 1. So the XOR is taking care of the bitwise inversion, because if we look at the truth table for XOR, zero, 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 one, 1, 0, 1, 1. If we think of, well, I'll call this B and control. If we think of our bit B, if it's 0 and the control bit is 0, the add subtract control bit is 0, then the result that's going to get passed into the adder is a 0, which we could just write as B, because that is what B was. If B is a 0 and the control bit is 1, then we pass in a 1, which is the same as B naught, right? So when the control is 1, it flipped B, and it passed in a 1 instead of a 0. If the control bit is 0 and B is 1, then we just pass in a 1, which is B. And if the control bit is 1, again, we flip B, it's B naught, which is now a 0. So I wrote this in the wrong order. So essentially, this control bit is going to flip B. So that's taking care of the bitwise flipping. And then it also provides a carry in of 1. So that's where we get the plus 1. So this thing is implicitly going to do your 2's complement conversion without having to do it manually. So that's what's really nice about this combined adder subtractor, is that you can do subtraction rather than addition by setting a single bit, and the XORs are going to take care of the rest. So what I would imagine, you might have a question that takes, say, gives you two 4-bit numbers, and you have to add them and trace where the bits are. And I know that question came up on the homework because I've had some people come in for it. So make sure you know how to assign your A bits are not going to change, right? Your A bits don't change. Your B bits are going to go into this XOR. So if your B is a negative number, then this whole line is going to be a 1. And whatever B is here is going to get flipped. So this is going to be B3 naught, B2 naught. So if B was 1, 0, 1, 1, we'd have a 1, 0, 1, 1. And if our control was 1, then these would be flipped. So the output of this XOR, 1 and 1 is 0, 1 and 0 is 1, 1 and 1 is 0, 1 and 1 is 0. Okay, so these are the bits that would actually go into your adder. And again, when the control is 1, that's going to be the carry in. So you'll have a 1, 0, 1, 1, 0, and then the result of this carry out goes to the carry in of the next one. So I hope you're familiar with these carry and ripple operations in the adders, because that's important for this class. I would imagine that a question like this might show up where you have to trace these bits, but it's really not that difficult as long as you understand what's going on with this add subtract control. All you do is set this to 1 when b is a negative number and 0 when b is a positive number. Okay? The next little bit is about flip-flops. So flip-flops, you don't need to know what's inside of a flip-flop for this class, but you do need to understand how they work. So you take, this is a simple example. They have an input, an output, reset, clock, and enable. So the important thing to remember is that if you're given a timing diagram, which I could imagine this being on the exam as well, is your Q, which is what you're going to have to trace, is only going to change on a rising clock edge if the reset is high or the enable is high. So if there's no enable and no reset, then it's going to change every single clock edge. Just D passes through to Q. But if there's a reset and on a rising clock edge, then your Q becomes 0 no matter what. If your enable is high on a rising clock edge, then Q becomes whatever D was. So let's look at this. Before we get our first rising clock edge, we don't know what Q is. But then on this first rising clock edge, there's the reset is high, so Q is going to be 0. And we don't even have to look at anything else until the next rising clock edge. We're going to look at this rising clock edge. And let's say, I mean, I drew it kind of wonky, but this enable isn't high yet, so enable is low, so we keep going until the next clock edge. Here at this clock edge, our enable is high, so whatever D is passes through to Q. The Q is going to go high in this spot. We don't worry about it until the next rising clock edge. Okay, where we see enable is low, that means Q doesn't change. Enable is low, so we don't worry about it. Next rising clock edge, our enable is high. So that means our D passes through to Q. Our Q becomes whatever D is at this point, which is a 1. And we already were a 1, so we don't have to worry. Next rising clock edge, our enable is 0, so we don't do anything. And our final rising clock edge, our enable is 1. So that means whatever D is passes through to Q. D is 0 at this spot, so Q goes to 0. So I would say make sure you know how to do these timing diagram questions. In this bit case, even if you have no enable, then you just every rising clock edge, you just pass D through to Q. And reset is probably just going to happen at the beginning, is usually what happens. And remember that initializes your Q to 0. So you technically don't know the value of Q because these things have 2 stable states. It could be 1 or a 0 before anything has happened. So you usually initialize it by resetting it to set it to 0. And then it depends on your enables and your D. The next example is we have a hex. This is a register instead of a single flip-flop. So this would be a series of registers all getting loaded with a string of bits at the same time. So the idea is basically the same. Instead of enable, we call it load. You might see this as load, right? We still have a reset. We still don't know until we've initialized it. So on this rising clock edge, our reset is high. We call this hex 0. And these are just going to be hex numbers. And we look at the next rising clock edge. Let's call this load high here. If load is high, then D passes through to Q. So our Q becomes hex A, 0xa. That's what was stored in our D, or it passed through to the load. So sometimes when you see these timing diagrams, you'll see a little bit of a transition period. And that just comes from the internals of the gates and everything. There's a little bit of a rise time and a fall time. So when if a rising edge intersects right on one of these things, then it's unclear what's going to happen because some of the bits may have transitioned and some of them may have not. I would assume that for your class, it's not going to happen that a rising clock edge is going to intersect one of these things. I would say just do your best, eyeball it, try and pick whichever one makes the most sense. So if this rising clock edge happened right here and we assumed load was high, then it would pass through this hex 4. But let's keep going. So the next rising clock edge, we have the load is high and an E is in there. So we're going to change Q to be XE. Next rising clock edge, our load is 0, so we do nothing. Next rising clock edge, our load is high. That means we're going to pass the hex 5 through. 5. Next clock edge, load is 0, so we do nothing. And then the one after that, our load is high. So we're going to transition to XB. Okay. So this is all you have to do for these ones. It's really not that bad. You just look at what's in the D, you pass it to the Q. I would imagine that a timing diagram question like this, like one of these or maybe both, will be on your exam. For memory, so there's not a whole lot that I can really cover that's not just in your slides for this memory. I know there's a whole lot of stuff about which type of memory to use for which application. I would say just review the slides and make sure you understand all the different parts. So in general, RAM and ROM is going to be called like M by N, where M is the number of addresses or rows, and N is the number of columns or bits in each row. So if it's an M by N ROM, then you really have N times N number of bits stored in there, where M is the number of addresses and N is like the bus width or the data width. Okay, so make sure you understand how that works. And the difference between RAM and ROM is RAM is going to have a read and a write, whereas ROM is only going to have a read. So they're not even going to be a read-write select pin. It's just going to be reading because you can't change ROM very easily. And a register, again, is kind of like RAM, but faster. So you're going to be able to write and there's a write side and a read side. So you can write, choose an address and enable, and you can read, choose an address and enable, all in the same clock cycle. So that's the benefit of register files that allows you to do that stuff more quickly. But again, you're going to need to know the trade-offs. So my recommendation would be to review that slide from chapter 3 that has all these different memories on here. And the most important things, right, are knowing what's more expensive and what's less expensive. So know the trends. Register file is the most expensive. It's the fastest, it's the largest, and it's the closest to the CPU. It's stuff for like temporary quick calculations, but you're not going to be storing a whole lot in a register file because it might be just bits, instead of bytes, megabytes, gigabytes. Whereas RAM is where you're going to be storing most of the memory for your program that's running. There's two types of RAM, SRAM and DRAM. And I think you might need to know about the transistor level of these. So just remember the difference between the two. SRAM is the faster, more expensive one used for things like CPU cache. So these are things that are being accessed by the CPU very frequently and need to be very quick. Whereas DRAM is like your main RAM, your main memory that the active programs are loaded into. So the real quick summary of DRAM, the way DRAM works is you have this transistor that when the word enable is high, this transistor basically closes and connects the output of this capacitor to your read and write port. So there's going to be a charge stored on this capacitor, either a 0 or a 1. And when you enable this, when you turn on this transistor, that 0 or 1 is going to propagate through to the other side. So if you're reading, you're going to be sensing what this voltage is. Open this up, or close this switch, and sense whatever voltage is stored on the capacitor. And if you're writing, then you're going to assert a voltage at this point, turn on the transistor, and let that voltage propagate through the capacitor. So if there's a 0 stored here, and you assert a 1, then turning on this switch will cause this capacitor to charge. Similarly, if you're reading it, you can sense the voltage here. Turn on this transistor, and if there's a 1, then that 1 will propagate through to the other side. To make sure you understand how this works, the disadvantage of DRAM is because there's a capacitor here. If there's charge stored on this capacitor, there's going to be a little bit of leakage every once in a while, either across the capacitor or across the transistor. So eventually this voltage, the amount of charge stored here, will decrease. And so they have these refresh cycles. So every once in a while, you need to go through and refresh the charge on this capacitor to make sure that if it's a 1, that it stays a 1, and if it's a 0, that it stays a 0. To make sure that charge leakage isn't ruining what you have stored in RAM. SRAM is a little bit more complicated, but it's pretty simple when you actually look at it. So this is the complex transistor network, but it simplifies down to just these two inverters kind of opposite each other. So when we initialize it, if we assert that there's a 0 here and a 1 here, this works out it's stable in both sides because this 0 will get inverted to a 1, and this 1 will input here, and get set as a 0 there. So this is a stable configuration. When we're reading, you can enable this word line and have these values propagate out to the bit line which you're reading from. And if you want to store a value, you can assert a voltage here. So if you want to store a 1, this is our Q. This is where the actual bit is stored. If we wanted to store a 1, we can load a 1 onto this line and a 0 onto this line. And then turn on our word lines. And what'll happen is this 1 will get passed through, enter into this inverter, and then a 0 will be on the output. Meanwhile, this 0 is going to pass through and confirm this 0. So there's not going to be any fighting between the voltages. There's going to be some losses in this transition from a 1 to a 0, but I think they minimize it by preloading a 1 volt or like a logical. If your logic is 3, or 3.3 volts, they'll preload like logic over 2, so like a 1.6 volts onto this line, and then the transition speed will, instead of having to go from 0 to 3.3, it'll go from like 1.6 to 3.3. But I think that's a little bit about the scope of the class. So for now, just make sure you understand the structure of this thing and how you can read and write it by either asserting a voltage on these lines or by sensing the voltage on those lines. Okay. Yeah, and of course, the inside of this SRAM is, each of these is 2 transistors, so that's a total of 6 transistors to do it in this way. The other types of ROMs that you covered, I would really recommend just going over your slides because all of the information that you might need to know is on there. So I've copied some of it down here, but remember your one-time programmable ROM, it's basically hard-coded. You either blow the fuse or you don't. You'll hard-code a 1 to the side of the transistor. So if you turn on this transistor, then a 1 will pass through the fuse and appear here. If you blow the fuse, that makes an open circuit, and so there's going to be a 0 on this line. So this cannot be reprogrammed, but it's very cheap because all it requires is a fuse wherever you need a 1. There's the other types of ROMs, there's EEPROM, EEPROM, and Flash. Make sure you review the differences between these things. EEPROM and Flash are a little bit more modern. EEPROM is, you're probably not going to see that anywhere unless you're working on something that's very old. EEPROM is nice because it's electrically reprogrammable, and Flash is nice because you don't have to reprogram word by word. You can reprogram entire blocks at a time. So I would say review your slides and make sure you know exactly all of this stuff, but this is most of what you need to know for memory, I think. There's 2 more little circuits, the array multiplier and the shifters. So this shifting and adding is kind of what I was talking about earlier, where you're going to notice that when you're multiplying 2 binary numbers, the original number, the top number, reappears several times in the partial product. And each time it's bit shifted to the left a number of places, and those number of places are determined by where the 1s are in your second number. So we can see that this number is the original number bit shifted 0 times. This is the number shifted left 1 time, and this is the number shifted left 3 times. So working in binary, shifting left once is the same as multiplying by 2. Shifting left 3 times is the same as multiplying by 2 3 times. So this is how you can implement multipliers using bit shifters and adders by shifting a number of times equal to how many 1s are in the second number, and then just adding all of the results. So that's a little bit simpler than doing the piecewise multiplication like we do by hand. The array multiplier, I don't know if you're going to have a question about this. I don't know what kind of level of detail you talked about this in class, but this is in your slides. I would say study this, but like to understand what's going on here, you kind of have to look into how multiplication works bit by bit. If you notice, the first bit of multiplication is the first bit of each multiplied together, and then the rest is going to be zeros. So if we looked at the first bit of our result, we can say that that's just A0 and be 0. Because if they're a 1 and a 1, then our first bit is going to end up being a 1. And if they're a 1 and a 0, then it's going to end up being a 0. And likewise. So that's why the array multiplier has just a simple AND gate for this first bit. And then the structure of it kind of looks similar to when we look at a product, and it kind of shifts to the left each time because we just have zeros filled in here. But that's essentially what's happening is you're adding the bits a certain number of times. So this you'd be adding 3 bits together, chaining down to get this result, and then the carries are going to propagate to the next column. So I would say look at this. I don't know if this is going to be on your exam or not, but if you have any questions about this, you can ask. Otherwise, I think we've covered a lot of the stuff that is possibly be on the exam. So the biggest things I would say is understand how these systems work kind of at a higher level, like be able to describe what they do, probably more so than knowing what the insides of them look like. And definitely make sure you're comfortable with your binary numbers, 2's complement, multiplication, and the fractions. I can guarantee that there's going to be some problems where it says write a binary fraction like this. The last thing is rewriting circuits using universal gates. So I guarantee there's going to be a question like this. You might need to count up how many gates you use at the end. But make sure you're comfortable with these things. Other than that, I think that's most of what's going to be on this exam. So are there any questions? Things that I didn't cover? Okay, if there's no questions, we can call it for today. Let me know if you have any other questions. Otherwise, good luck on your exam, and I hope you do well.